Hello and welcome back. Let's continue with our lecture on mathematical methods. Today we are going to cover two important topics mutually connected with each other. One is a definition and classification of singularities of a complex function, and second and most important theorem in the complex analysis is Cauchy's residue theorem. And today we are going to cover that. Let's continue. This is a part of course PH3103 at IISER Kolkata. The first topic we are going to look at today is about Taylor's theorem. Let's start with this. Let f of z be analytic in a domain D. Let z naught be a point in D. And then f of z has a series representation given by f of z is equal to some k going from 0 to infinity fk k z naught divided by k factorial into z minus z naught to the power k. Here f of k stands for kth derivative of function f of z, and this is what we call a Taylor series or series representation. It is valid for the largest circle C with the center at z naught and the radius r that lies entirely within D. So this is what is called the radius of convergence of the Taylor series. The proof is rather simple. It is rearranging Cauchy's theorem. We have seen in the last lecture nth derivative of analytic function can be represented using the Cauchy's integral formula. Of course, if you are exactly looking at the proof, I recommend you this step between the Cauchy's theorem and the Taylor's theorem, and you have a rigorous proof of Taylor's theorem. Let's go ahead with the singularities of function f of z. If a complex function f of z is failed to be analytic at a point z is equal to z naught, then the point z naught is said to be singularity or a singular point of the function. I was a bit tired all throughout saying that non-analytic, not analytic, sometime even fumble to say it is analytic even if it is not analytic, because the term of singular or a singular point is not used. Once we know that the point which is not analytic, we can call it a singular point or singularity. That is what we are going to talk about in today's lecture. Now let's take a quick example. You are all familiar with the singularity. I don't think there is need to be any formal definition. The example is simple 1 by z at z is equal to 0 is a singular point because it is not analytic and more or less takes an undefined value for the function. So it is naturally a singular point. Now from this definition, it is not necessary function to blow up to be singularity. It just should not be analytic. It will not satisfy the Cauchy-Riemann condition. That's all it says. But often we encounter this 1 by z kind of a thing, which is a singular point. Now comes type of singularity called the isolated singularity. It is obvious, but let's look at the definition first. Suppose that z is equal to z naught is a singularity of a complex function f of z. Then the point z is equal to z naught is said to be isolated singularity of the function f of z if there exists some deleted neighborhood or punctured open disk such that 0 less than z minus z naught mod is less than r. That basically means that the neighborhood of z naught with the radius r around z naught through which f of z is analytic. Let's try to see it more pictorially. And how do we have a domain in which the function f of z is defined, and that function z is analytic most of the point except one point z naught at which it is not analytic. Then what we do is we construct a neighborhood around z naught with radius r and punch it off, and the rest of the point, if f of z is analytic, then we call such singularity as an isolated singularity. So basically you should be puncture a hole through it and able to remove the singularity, then it becomes the isolated singularity. Let's look at some of the examples. The easiest example for isolated singularity, we can think of any polynomial function or analytical function f of z and divided by z minus z naught to the power n. If f of z is an entire function, for n greater than 0, z by z naught is a singular point. Now it is very clear we can remove a small neighborhood around z naught, and then rest of the point, the function f of z is well behaved and that is analytic, and then this becomes an isolated singularity. So look at the function f of z is equal to z by z square plus 1, and now we have a 2 point at which there are singularity at z naught is equal to I and at z1 is equal to minus I, that is plus or minus I, the denominator goes to 0, and these are the point h function fails to be analytic. We can again punch hole through this point given when z is equal to I and z is equal to minus I, and then we can eliminate a small neighborhood around that, and that is what we call is a puncture or hole, and the rest of the domain function f of z is equal to z by z square plus 1 is an analytic once you remove these two holes or punctures around z is equal to plus or minus I, then what we call is these two singularity are isolated singularity, and the rest of the point function behaves reasonably well. Now comes the Lorentz theorem or the Lorentz expansion. It is very similar to the Taylor expansion. In Taylor expansion, we have seen the function is represented as z to the power n, where n goes from 0 to infinity. That means all the few powers of n, and that is how we know that function is analytic, because there is no 1 by z minus z naught or any other power. So now next comes is a Lorentz series which has a both positive and negative power. Let f of z be an analytic function in an annular domain D defined by z minus z naught is greater than small r and less than capital R. Then f of z as a series representation given by f of z is equal to k going from minus infinity to plus infinity, ak f of z minus z naught to the power k. Now you see the important difference between the Fourier series and the Lorentz series is that in the case of Lorentz series, k goes from minus infinity to plus infinity. In the case of Fourier series, k goes from 0 to infinity. When we have k goes from 0 to infinity, we have only positive power and a constant. That makes the function is completely analytic. In the case of Lorentz, there are negative powers of z minus z naught. We can clearly see that this function is not going to be analytic at a point z is equal to z naught. Now the valid region for this expansion z minus z naught is in an annular region with the inner radius small r and outer radius capital R. The coefficient ak are defined by ak 1 by 2 pi I integral over a closed contour f of s minus z naught k plus 1 ds. Again, there is a familiarity what is coming from the one of the Cauchy's theorem. In this case, what we have seen is a z minus z naught is also present, and that is one of the way to prove it. We will not really go over the proof of these things. So we have the value of k here 0 plus or minus 1 plus or minus 2 etc. That means k goes minus infinity to plus infinity. The region here is an annular region. Now here C is a simple closed curve, lies entirely in the domain D, and we have z naught inside that region. Let us look at this pictorially. We have open disk or neighborhood R around the point z is equal to z naught. We have a inner region small r. So we are interested in the annular region between small r and capital R. This is the region where we expand our function, which is completely analytic in this region, and then we can expand this around the point z naught as a series expansion given here, and where coefficients a, k are given by this integral. Ak is equal to 2 pi I integral over closed curve f of s divided by s minus z naught to the power k plus 1 ds, where the contour C should be lying here entirely within this region, and it should also enclose the point z naught. That means to say we cannot simply take a contour something like this. This kind of a contour is not allowed. The contour should contain the point z is equal to z naught. So this is essentially what is a Lorentz series. Let's quickly look at the example for Lorentz series. Often we don't use the cumbersome integral and all that thing to or evaluate the Lorentz series. What often we do is the simplest way of expanding such thing using the binomial expansion. You have to suitably adjust to get the proper binomial expansion. Let's look at the example. Let's expand function f of z is equal to 1 by z minus 1 in a Lorentz series in the region between 1 and 2, and that is what we are interested in. So let's first pictorially see the domain what we are interested in. The function has singular point at z is equal to plus 1. So I pointed here z is equal to 0 also. There is no problem there. It's not a singular point. The singularity is only at z is equal to plus 1. So next we take a point at z is equal to 2. That is our z0, and that is where we want to have an expansion. So we draw the annular region with the radius 1 and 2. So that means that the first one passing through z is equal to 1 and second one is a passing through z is equal to 0. Now as per this theorem, it is sufficient to have your function to be analytic inside this domain. We don't care whether function is analytic or not on this boundary, so that is fine with us. As long as it is analytic inside this domain, it is interior to the annular region, it is fine with us, and then we can expand. The main trick to do is, of course, that integral and all that thing, but one doesn't go through that. The simplest trick is to do the binomial expansion. Here you can take somehow shift the center z is equal to 2, and then you can write down the expansion. So let's rewrite the function given to us in suitable way. So we write f of z as a 1 by z. To make it around z is equal to minus 2, we add 1 and subtract minus 2, and then we can see that z minus 2 becomes a common factor, and you can pull it out, and then you have a function which is 1 by 1 plus 1 by z minus 2. Now we see that this is a small quantity, and then you can do a binomial expansion and go ahead and do that. Then you have the expansion of this with the 1 by z minus 2 outside, and you do a binomial expansion, which is straightforward to do. In this case, you have it as a Lorentz series. So this is a way one can take a conventional approach. One can do the integral g of s minus z0 to the power k plus 1 and ds. This integral one can do and do all that, but the easiest way is to do proper expansion. For example, if you have given a function sine z by 1 by z. So easiest way to do is 1 by z, you know how to expand sine. So that is something like z minus z cube by something like 3 factorial, I think, so on. And then you see the expansion is already given. So this is how an easier way of doing. One can follow proper rules, but often it leads to tedious step to do that. This is advantage is that we can employ already known things to our complex analysis. It is going to give you correct expansion, as we have already seen that in the real analysis, and that is why it is much more useful to do that way. Now there is an homework which is a much easier one. You have to expand the function f of z is equal to 1 by z into z minus 3 in the Lorentz series in the circle around z is equal to 0 with the radius 3. Again, I want to emphasize that you don't care whether function is analytic or non-analytic on the circle, but it should be analytic inside the annular region, and that is suffice to have a Lorentz series. And you can do this and write it on a paper and upload on VLearn. We have already understood there is something called isolated singularity. There are singularities which are not isolated. They are branch cuts and similar, which are continuously distributed along a line. So such things are not isolated singularity. We can further classify the isolated singularity. The main intuition comes from the fact we have seen one of the Cauchy's theorem that integral over a circle around the function f of z is equal to 1 by z minus z naught to the power n is equal to 0 for n not equal to 1, and it is equal to 2 pi for n is equal to 1. So this gives an important difference between 1 by z and the rest of the power. So this leads to further classification of an isolated singularity. Let's have a look at it one by one. An isolated singularity at a point z is equal to z naught of a complex function can be further classified based on how it is expanded in terms of Lorentz series. The first one, of course, is called the removable singularity. The removable singularity looks like there is a singularity, but there isn't really a singularity. That means you may have a function, something on the numerator and something on the denominator, and the factor in the denominator might go to 0 at some point, but Lorentz series actually does not have any of such irregularities. That is a way, formally, to say that the Lorentz series, if the coefficient of a minus k for k greater than 1 are 0, and such singularity is called the removable singularity. For example, the function f of z is equal to sin z by z that can be expanded in terms of a Lorentz series as a 1 minus z square by 3 factorial plus z to the power 4 by 5 factorial and so on. Now you look at the function itself, it looks like that at x is equal to 0 is going to be a problem because denominator goes to 0. However, when you look at the Lorentz series, that does not have any problem at z is equal to 0, and such type of singularities are called removable singularity. Now next comes the pole. The pole in a Lorentz series, if all the coefficients of a minus k are 0 for k greater than or equal to n, for some finite value of n are 0, then such singularities are called poles, and n is called the order of pole. That means when you have a Lorentz expansion, you have a term z minus z naught to the power n, and that for some finite value of n, it simply terminates, and all the coefficients a k are a minus k are 0 beyond some finite value of n, and such things are called the poles. So one of the easiest example is function 1 by z minus z naught to the power n, or another function is 1 by z naught. Another function is 1 by z minus z naught. Both these functions, beyond all n, there is no Lorentz coefficients there. You see there is only one coefficient, a minus n, that is equal to 1. Rest of all coefficients are 0. The second one is only a minus 1 we have, and that is equal to 1, and rest of are all 0. So this is called the pole. Another important kind of a pole which we come very regularly across the contour integral, which we call is a simple pole. In the Lorentz series of a simple pole, all the coefficient a k are 0 other than a minus 1. That is, you have a function of this type, 1 by z minus z naught, because a minus 1 is not 0. All other terms for negative coefficients are 0. So those are called the simple pole. That means in principle you should be able to write it z minus z naught plus some a0, a1 plus a1 into z minus z naught to the power 1 and so on. So this is what is the meaning of the simple pole. Let's all put into a kind of a table which summarizes the properties of an isolated singularity, which is essentially based on the Lorentz expansion. Now we have a removable singularity which can be easily expanded in terms of a positive power, or it looks like almost like an analytic function. On the other hand, you have a pole of the order n, then you have the lowest power z minus z naught to the power n, and your series, Lorentz series, terminate for the negative thing. All the negative coefficient greater than minus 1 are 0. Simple pole is just have a minus 1. Rest of them are all 0. So that is what is a more interesting case. And then we have an essential singularity where negative power goes all the way till infinity. It is not terminate any finite point. So that is what we call essential singularity. So the important three type of singularities are one is a removable singularity, other is a essential singularity, and then the pole of some finite order, including the simple pole. Okay, we had a good marathon with the singularities. Let's look at the what is called the residue. The residue is a specific coefficient of a Lorentz series, that is the coefficient a minus 1, that is of the form 1 by z minus z naught, is what we call is the residue of a function f of z for an isolated singularity at z is equal to z naught. The notation for that is either a minus 1 or specifically written as a residue f of z at z is equal to z naught. So this is a notation used. You can either use a minus 1 or you can use a residue f of z z naught. Okay, there are a simple way to compute the residue. The one of the easiest is to compute the residue of a simple pole. If a function f of z as a simple pole at z is equal to z naught, then the residue of that function is given as a limit z going to z naught, z minus z naught into f of z. So that is what is going to give you the residue. You simply have to multiply the function f of z by z minus z naught and take the limit z going to z naught will give you the value of the residue. Now the residue of pole of the order n can be determined in a similar fashion, but a little bit more involved. If a function f of z has a pole of order n at z is equal to z naught, then the residue of that can be calculated with the 1 by n minus 1 factorial limit z going to z naught, differentiate n minus 1 time with respect to z, the product z minus z naught to the power n f of z. So it says that you multiply the function with z minus z naught to the power n, then differentiate it n minus 1 time with respect to z, and then take the limit z going to z naught and then divide by n minus 1 factorial. So basically by doing this process you are trying to eliminate all other coefficients and then trying to reach the coefficient a minus 1 in the Lorentz series. That is what is gives you the value of residue. So these two are the very useful formulas to compute the residue of a function, either simple pole or of the order n. Homework problem: you have to calculate the residue of the function given below for all the poles. The first function is f of z is equal to 1 by z into z minus 3. The second function is 1 by z square minus 2z plus 2 square. So this definitely has a pole of order 2 and this has a two simple poles. It is straightforward to see. This is a quadratic function, so it should have two roots. You can already factorize that, and then you see that there is a whole square sitting there, and then write it on a paper and upload on to Wheeler. That seems to be a domain coming. So now we get to one of the most important theorem in this part of course, that is called the Cauchy's residue theorem. The Cauchy's residue theorem is probably as important as a Cauchy-Riemann condition. So sometimes it is also called the residue theorem. Don't have to really bring in Cauchy here, but we might as well bring in here. He is our mathematician of the fortnight. So we are going to talk about Cauchy as much as possible. Let D be a simply connected domain C, a simple closed contour lying entirely within the D. If a function f of z is analytic on the contour C and within, okay, it has to be analytic on and inside, except at the finite number of isolated singularities z1, z2 and so on till zn, then we have integral over contour C f of z dz is equal to 2 pi I times sum k going from 1 to n residue of f of z at zk. we might have expected this to happen. We have already seen some of the Cauchy's theorem eventually leading to this, which is the ultimate of all the theorems, which is called the residue theorem. Now carefully see that the function is analytic except few isolated singularities inside C. So we have very familiar with that. What is isolated singularity means? We can puncture that and then rest of the place it is fine. So this is exactly looks like multiply connected domain. So we have a domain D, that is what it was. It is a failed animation. So now we have a contour C in which you have a function which is analytic in most of the places except it has a few isolated singularity. What isolated singularity means? We can remove an open disk or a small neighborhood from that point and then get rid of it completely. Now we see that there are these contours C1, C2, C3 and Cn etc. We can immediately use the Cauchy's multiply connected domain. Now what it says is that we have a contour C and then we have a smaller contour which are all disjoint, don't have any common point. You will have to construct C1, C2, C3 such that they don't have common point. And then the function is analytic outside all CKs. The function f of z is analytic outside all these contours C1, C2 and Cn, but it is inside contour C. So now we can simply use the Cauchy's theorem and we say that the integral over contour C f of z dz is equal to k going 1 to n integral over contour ck f of z. Now we know that the integral is simply the residue of the function that we can again come from the Cauchy's theorem. This is going to be the residue of the function zk. It is rather straightforward to do that. I recommend you do this and then confirm yourself that you are going to get residue of the function at zk. So take an example where we have to compute the integral using the residue theorem. Let us evaluate the contour integral of the function 1 by z minus 1 square z minus 3 dz using the residue theorem. The contour C is given as a rectangular box at x is equal to 0 to x is equal to 4, y is equal to minus 1 to y is equal to 1. We have the isolated singularity at z is equal to 1, we have a second order pole, and at z is equal to 3, we have a simple pole. Then let us see it on the complex plane. We have two singular points at z is equal to 1 and z is equal to 3, and then we have our contour which is mapped here at x is equal to 0 to x is equal to 4, and then y is equal to minus 1 to 1, and then we have to compute residue at the pole. Let's look at the first residue. First one is not a simple pole, that is a second order pole. So we have to use the formula given here. Residue of f of z at z naught is 1 by n minus 1 factorial limit z going to z naught dn minus 1 by dz n minus 1 z minus z naught to the power n f of z. So here n is equal to 2, so we have to differentiate it once. The second one is fairly straightforward. It's a simple pole. All you got to do is multiply by z minus z naught and take the limit z going to z naught. So once we do this calculation for the first one, so we differentiate this 1 by z minus 1 once and then take the limit z going to z naught, then we get residue to be minus 1 by 4. On the other side, at z is equal to 3, we get residue to be 1 by 4. This turns out to be same number, and then we can sum them up and multiply by 2 pi I, and that would be the value of integral which goes to 0. Again, in this case, the contribution from both the singularity somehow cancels out with respect to each other, and we get the contour integral to be 0. So this is how we use a Cauchy residue theorem to evaluate the integral over a closed contour enclosing that. Now let me stop here and continue with the next lecture.